Okay, so section 11.5 on perimeters and areas of similar figures. We'll start off with a couple of examples. If we have a regular triangle and the apothem is equal to 1, draw that. This length is 1. I can draw on that segment as well, and this creates a 30, 60, 90 triangle with 1 being the short leg. The long leg then would be root 3 times that one, which would make this root 3, which makes that length root 3, which makes 1 complete side of the triangle equal to 2 root 3. Then we have a special formula for the area of a regular triangle. I'm going to take the length of that side, squared root 3 over 4, and that's going to simplify all the way down to 3 root 3. And the next example, same exact drawing, this time the apothem is equal to 3. So the method I'm going to use is exactly the same. From the short leg to the long leg, we multiply by root 3. So 1 complete side is 6 root 3. So then we're going to take the length of that side, the 6 root 3 squared times root 3 over 4. And that gives us 27 root 3. If we have a regular quadrilateral, the apothem is 2. Normally we don't talk about the apothem of a square. That means that each side of the square is equal to 4. So then the area is equal to 16. And the next one, if the apothem is 3, then each side is 6, so our area is 36. And the last one, if the apothem is 4, each side is 8, so the area is 64. And we can start to look at a pattern in these. The method is going to be exactly the same. And if I wanted to, I could start establishing some ratios between the linear ratio, comparing the lengths of the corresponding sides with the ratio of the area. And we'll look into that here in just a minute. The process for finding the area and perimeter of a regular nonagon is going to be the same for each one of those. For this time, we have an apothem equal to 1. So we will draw in that segment. In a regular nonagon, the sum of the interior angles is 1,260. Divide that by 9, so each angle is 140 degrees. When we draw on this radius, we bisect it to make that equal to 70 degrees. The tangent of 70 is equal to opposite over adjacent, multiply by x, divide by the tangent of 70. So x is 1 over the tangent of 70. That's half of one side. So if we multiply that by 2, we get 1 complete side. Multiply that by 9 more to get the length of all 9 sides. And we would get 18 over the tangent of 70 for the perimeter in this one. I might as well go to the other one that has the apothem of 3. The process is going to be exactly the same, except the x value will be 3 times bigger, which means that the perimeter is also 3 times bigger. So the perimeter in this one is going to be 54 over the tangent of 70. Perimeter is a linear measurement. Whatever the ratio of the corresponding sides is also going to be the ratio of the perimeter. Going back to the first one, area is 1/2 times that perimeter times the apothem, and our apothem was 1. So if we multiply all this, we get an area of 9 over the tangent of 70. So here's our area. We already had our perimeter. For the bigger one, the area is 1/2 times our perimeter times the apothem, and the apothem in this one was 3. If we simplify this, we get an area of 81 over the tangent of 70. So we have area and perimeter for this one. Let's look at these ratios. Here is the ratio of the perimeters, and we have that 3-to-1 ratio. This is 3 times bigger than that one, and the linear ratio is also 3-to-1. And then if we want to compare the areas, the area is now in a 9-to-1 ratio. If we divide one by the other, it's a 9-to-1 ratio. So in general, when two shapes are similar, we have a linear ratio of A to B, and that's going to be for the corresponding segments, whether it's the apothems, the radii, any specific segments, that's going to determine our linear ratio. And then we also get an area ratio. For that, we square each one of those, and that's going to be the ratio of our areas. So A to B becomes A squared to B squared. Here's an example of how we would use that. These two shapes are similar to each other. We have these corresponding diagonals, so if we look at those, we can establish our linear ratio, 2 root 3 over 5 root 3, which simplifies down to 2/5. So that's the ratio of all the corresponding sides. I don't know the length of this segment or this other segment. However, what I do know is that they're corresponding to each other, and so they're going to be in the ratio of 2 to 5. I don't care about those lengths because they're not going to help us find the area. And in fact, I don't have enough information to calculate any areas. However, we are given the area for the one on the left. We're going to use that to our advantage. If the A to B ratio is 2 to 5, that means that the area ratio, A squared to B squared, is 4 over 25. So we're going to take what the ratio is, set it equal to the actual areas. So 6 over A equals 4 over 25. Now we can cross multiply. So 25 times 6 is equal to 4A. And we get that the area for this bigger one is exactly 37.5 units squared. We couldn't calculate the area directly, but we can use these ratios to help establish it. Next example. We have these two quadrilaterals that are similar. We have the areas for both of them. We have the length of 3, which is corresponding to x. From this, we want to find what is the length of x in this bigger one. Now I know that the linear ratio between them is 3 over x. So that means that the area ratio is going to be 9 over x squared. We actually have the areas, so we're going to set these two fractions equal to each other. 360 over 49 divided by 40. So the actual areas is equal to the ratio of the areas. With this, we can cross multiply. 40 times 9 is 360. Multiply in the other direction, we have 360 over 49 times x squared. We want to solve this for x, so multiply both sides by 49. Divide both sides by 360. X squared equals 49, which means then that x is equal to 7 units. Next example, we have some parallel segments, and because of that, we have alternate interior angles that are equal to each other, which tell us these two triangles must be similar. We can establish the linear ratio between them by comparing those two parallel sides. That's going to give us a ratio of 5 to 8. So the area ratio is 25 over 64. We'll take that ratio, set it equal to the actual areas, 10 over A. We don't know the area for this one on the bottom. Cross multiply, and we're going to get 640 is equal to 25A. And if we solve that for A, we get exactly 25.6 units squared. Got a few more examples. Maybe you want to pause your screen and try these on your own. The first example, we have a couple of quadrilaterals that are similar to each other. We have the perimeter for the big one, the area for the smaller one, and we can see the established ratio. So our A to B linear ratio is 3 over 1. We can set that equal to 22.2 over P. So the ratio of their perimeters is equal to the actual perimeters. Cross multiply and solve in that one, and we get the perimeter for the small one is a small 7.4 units. And then for our area, the A squared to B squared ratio would be 9 to 1. Set that equal to the actual areas. Now if we cross multiplied in this one, we would get that the area for the big one is 24.3 units squared. Second example is of the exact same type. And then here is our last example. All right, so we have these two different triangles. We have two isosceles triangles. These two lengths are 6 and 6, so those angles are equal to each other. And then angle D is equal to this angle over here. So we know that we have angle similarity. We have similar triangles. Because in the smaller triangle we have all three sides, we can use Hero's formula to find the length of all, find the area of this. So for that small triangle, we can calculate the semi-perimeter. 6 plus 6 plus 5 divided by 2 is 17 halves. Then use Hero's formula to calculate that area. And here's our area for the small triangle, triangle BED. That triangle is similar to the entire one, and as I look at that, the linear ratio is going to be 5 over 6. 5 is the base of that triangle. 6 is the base of the bigger one, which means that the area ratio is going to be 25 over 36. Now we can use that to our advantage. The ratio of the areas is equal to the actual areas. So the 5 root 119 over 4 divided by the area of the second one. Cross multiply and solve it. I'm going to try to make this a little bit simpler. I'll divide this numerator by 5, divide that numerator by 5 because they're smaller numbers. When we cross multiply, now it's 5a is equal to 36 would go up in this numerator when we cross multiply. 36 over 9 is 4, so it's 4 root 119. Then divide both sides by 5, and we get this for the area of the big one then. So area for the big entire triangle is 9 root 119 over 5, and the area of triangle BED is 5 root 119 over 4, and this section is all about similar shapes and finding areas and perimeters.